So this one is on the universal law of gravitation, and we're just continuing on with our ideas of rotation, same kind of ideas. So I'll be able to understand the universal law of gravitation. We're going to take notes from a video, review problems with peers, and discuss examples with group members. So because of Newton's third law, everybody in the universe exerts a force of attraction on every other body. Okay, and when I say everybody, it means every body. So it could be a box, it could be a rock, it could be something else. So this is Newton's universal law of gravitation. The force between two objects due to their masses is called the gravitational force, in which we are going to mark it as F of G. In this case, it's not the Earth specific, and it's not the 9.81, so that's a no-no. So this time we have F of G equals the universal gravitational constant, the mass of one object, the mass of a second object, and then the radius squared. So here we go a little bit more in depth. Our universal gravitational constant is 6.67 times 10 to the negative 11 newtons per Newton meter squared over kilogram squared. I am having issues with English. So if you notice, G is our 6.67. Our M's are masses of the two objects. We can also put this as M1 or an M2. Okay? So the radius is the distance between them, and we are going to square that. So let's look at our example first. So what is the gravitational force between the Earth and the Moon? So we have 6.0 times 10 to the 24th, and that's this one. And then we have 7.4 times 10 to the 22nd. That would be this one. Our radius is 3.8 times 10 to the 8th, 6.67 times 10 to the negative 11. So remember, when we're using the calculator, we have to do these keystrokes. We have to do second, and that is my comma, and that should give you an E. Okay, so when we're doing this one, it's just a straight multiplication. So after multiplying, we have G, which is our 6.67 times 10 to the negative 11. Mass 1 is 6.0 times 10 to the 24. And mass 2 is 7.4 times 10 to the 22nd. We end up with an answer of 2.05 e to the 20. Or this is also times 10 to the power of 20. Okay, so using your calculator, because there's going to be no other way we can do this one easily. Okay, so same idea. We had the mass of Earth, which was this one. We had the mass of Venus, which was this one. And all we do is plug in the numbers. And it leaves us with a number 1.386 times 10 to the 18 newtons. So there's also a way to determine the gravitational field around one object. So we take our universal law of gravitation and we change it to weight. So weight is equal to mg, and we're left with this derivation of a formula. So our m's cancel, leaving us g equals, or the gravitational field, let me move that up. Right, or the GFS, right? We'll call it the GFS. Is equal to gravitational constant times the mass divided by the radius squared. Okay, so what is the gravitational field strength in Earth? So we have a radius of 6.37 times 10 to the 6th. So in order to get this, we have to get GFS equals G times the mass over r squared. So let's look back. So gm over r squared, and we know that the mass of Earth is 6.0 times 10 to the 24th. So let's write that down. So mass of Earth equals 6.0 times 10 to the 24th. And then g is our same constant, so 6.67 times 10 issues, negative 11. Okay, so all we're doing is we take these numbers and we plug them in, and when I do this I get an answer of, here are my clicks here, so 6.67 second e negative 11 times the mass 6. So after all that click in, I get 9.86. Ooh, and no exponent. Fantastic. So I get a gravitational field strength of 9.86. Okay, so same idea. I still need my 6.67, but I need the mass of the moon, so let's click back. Mass of the moon is 7.4 times 10 to the 22nd. So let's type this in here. So mass of the moon equals 7.4 times 10 to the 22nd. So again, we're just using g times m over r squared. So let me click this one in. So my setup, we have g, we have mass of the moon over r squared. So we get a grand total of, let's type this so you can actually see the numbers instead of my nasty ass writing, 290,341.177. So that's what we get as the gravitational field strength of the moon. Awesome. So a couple notes here. Both the universal law of gravitation and the gravitational field strength follow the inverse square law. So if the distance between two objects is doubled, the gravitational attraction is 1/4, so it's less. So the gravitational field strength, if we travel beyond the Earth by a distance that is double its radius, then we only feel 1/4 of Earth's gravitational pull. So, for example, my gravitational field strength is 9.81, and if I move out, it's a quarter, and I go further, so the power of gravity is less and less and less. And if we keep looking at this, so distance from our mass, our gravitational field strength is very high, and as we go further away, look at the strength of gravity. It goes very, very low, and we're at caca levels. Okay? So, example 5. The gravitational attraction between Earth and Mars is 8.7 times 10 to the 16th. The distance between the two planets is 5.5. Earth has a mass of 6.0 times 10 to the 4th. What's the mass of Mars? Okay, so let's go back to our formula. So we have G M all over R squared, and that gives us our FG. But this time we have to solve for one of the masses. So I'm going to call this one Earth. Okay, this one that I've put a green over is Earth, okay? So the way we do this is we need to bring the R squared over. So we have FG times R squared equals GMM. And we still need to get M by itself. So we're going to divide by G and M. So we have G and M on the bottom. And these cancel. So we're left with M. So in this case, we're just going to plug it in. Our F in this case is this one. Or FG, excuse me. R is still this one. G is our 6.67, and then our mass is here. So after we do this, let's look what we get. So F of G, 8.7 second e to the 16 times R squared, which is 5.5 times 10 to the 10. Okay, and now we divide by 6.67 second e negative 11, which is also times . So after clicking that in, we get a 6.58 times 10 to the 23rd. Woohoo! Joy to the world. There it is. Love it.